So my name's Dr. Michaela Pollock, and I am Associate Professor teaching here in the Department of Chemical Engineering at UCL. And I'm here with my colleagues who are, as Lizzie has mentioned, part of the design team. So that is Dr. Ademola Odunsi and Dr. Richard Nyack-Luke. As we will be presenting some of the work that we do, as entitled here, about sustainability in chemical engineering design. And this work is also put together with our colleague, Dr. Shakira Badmos, who contributes to the teaching of this module as well, and the ideas and so on that we're presenting, but is unable to be here with us today. So as a start, I'm going to move on to the next slide, please. And you can see this is the outline for the presentation that we're going to have today. And our presentation is really split into three aspects, with each speaker taking on one of these three topics. So firstly, I'll be going through chemical engineering design. What is it, and what is its relevance to sustainability? And then I'll move on and to Dr. Ademola Odunsi, who will be talking to you about sustainability and how we've incorporated that into the design project brief that we had this year. And then also finally, we'll move on to Dr. Richard Nyack-Luke, who will be talking through some examples of the sustainability analyses that the students have been performing. So if we move on to the next slide. Thank you. So this is really the opener for then my segment of today's presentation. The introduction is over. And I will be looking at design, chemical engineering design, and its relevance to sustainability. So if we move on here now to the next slide, what is chemical engineering design? So firstly, the first animation shows us that really, as chemical engineers, we're thinking about raw materials. We're thinking about raw materials and how they're sourced. So the example photographs here are showing natural gas pipelines, and they're also showing biomass pellets. And the question is, how is raw materials such as the ones I've shown here sourced? How are they obtained? And what can we do with them? Yes, exactly, the products on the market. So in this slide here, I'm showing you some of the potential products that chemical engineers are involved in developing. So in that tractor there, we've got fertilizer being used. So chemical engineers design processes to make fertilizer, and also Lego, the Lego that you might remember, playing with or still play with at home. The plastics, the material involved in that is involved. Chemical engineers contribute to the production of that. And as it says here, it's not just the products that are relevant to chemical engineers and design. We're also interested in the market and the commercial aspects, and is there demand? So then what is chemical engineering design? And the next part of the animation shows this. And it basically shows that chemical engineering design and chemical engineering, they are the process building blocks. So how do we get from those raw materials to the end products? And we go through a design cycle, and that design cycle builds up in complexity. So we're going from conceptual design, where we're trying out a few different ideas, to preliminary design, where some more concrete calculations are being performed, and then onto detailed design, where really quite detailed, accurate calculations are being made. And on the basis of that, chemical plants are being built. And as it says here, as you're going through the process design cycle, you're adding more layers of detail. But something that we really want to highlight to you today is that sustainability, as well as safety, are embedded throughout this process design cycle. And if we move to the next slide, then my next question that I said I would tackle in this part of the presentation is, what is sustainability? And I believe some of you may already be familiar with the UN Sustainable Development Goals. And if not, there's a webpage that you can look at the bottom of the screen to read up on it a bit more. But in the UN Sustainable Development Goals, they set out a number of criteria, a number of goals that we need to be working towards to have a sustainable future. And some of these, we haven't highlighted all of them here in the slides today, but some of them we've highlighted. So climate action, for example, or responsible consumption and production, or sustainable cities and communities, then industry, innovation and infrastructure, and affordable and clean energy. And we feel that these ones in particular are related or are a relevance to chemical engineering design. So if we move to the next slide, then you can see some suggestions, and this is not a comprehensive and complete list, but this is just some suggestions of how chemical engineering design is relevant to sustainability. So in terms of climate action, chemical engineers can be contributing by considering how to reduce CO2 emissions. In terms of responsible consumption and production, chemical engineers would be, through that process design cycle that I've been outlining, trying to design processes where there's a reduction in energy consumption and also a reduction in the amount of waste that's being produced. Then in terms of sustainable cities and communities, chemical engineers can also be involved in considering the location of their chemical plants, potentially how that is situated with regards to sourcing of raw materials, and also the impact that has on communities. And then in terms of industry, innovation and infrastructure, chemical engineers can be thinking what kind of products are needed now? How can we address the challenges of the world at the moment?
I'll say thank you to Michaela for the introduction. My name is Ademola Ojensi, and I'm also part of the teaching team on the design project. And in particular today, I'll be talking to you about sustainability in the design project brief. So, at the start of the academic year, we hand students a project specification or a project brief, which they're going to have to work on throughout the rest of the academic year. And the students serve as contractors on the project, while we, the teaching team, and of course the wider academic team in the Department of Chemical Engineering here at UCL, act as members of the Bentham board because our company is styled as Bentham Corporation. And in this design brief, we give students the opportunity to start thinking about sustainability right from the word go. And there are various opportunities within the project lifecycle where they can actually embed sustainability. And I've tried to identify a few of them here. So, I mean, starting right from the raw materials or the feedstock, which they're going to be using for producing their end chemical, they can think about how sustainable the raw material is. Next, the final chemical products which they're actually going to produce, they think of the end use of these materials and how sustainable that will be. Next, they also look at where they situate or where they locate their plants in terms of available resources to them. They can also think about the powering of the plant, whether they decide to use fossil fuels or renewables or indeed a hybrid. They also think very carefully about the energy footprint of their process and try to minimize that through energy recovery. And finally, they look at various sustainability indices or metrics where they can qualitatively and quantitatively assess the impact of the process plant they're designing on the environment, the society, and so on. In particular, in this year's project brief, we gave students the starting materials of ethylene or ethane gas, as you may know it, and oxygen gas, which in the presence of silver as a catalyst, they react together to form ethylene oxide. Now, ethylene oxide is an intermediate which we expected all the students to produce. And from then on, we gave them the free hand to decide what further chemical products they could make from ethylene oxide. And there is a wide variety of chemical products that could be made from ethylene oxide. And I'll just highlight just a few of them and what they could be used for. So there's the ethylene glycols, which could be used in antifreeze, hydraulic brake fluids in cars and paints. There's ethylene carbonate, which is quite an interesting one because it's a crucial chemical in the production of the electrolytes used in lithium-ion batteries, which are very instrumental and useful in electric vehicles. Ethoxylates are also quite important because, I mean, it's a crucial component of shower gels, hair shampoos, and other cosmetics. And there is, of course, a wide variety of other chemicals which students could have chosen to produce from the intermediate ethylene oxide. Next, we've got students to also think about where they were going to locate their plant and how they were going to power that plant. So in terms of location, the Bentham board, which is our teaching team, specified 2 locations in Australia and in India. And of course, there were a variety of resources available in both locations, and students had to work through what was available to them and thinking about, I mean, the sustainability of the process they wanted to put together to eventually settle on a particular location for their plant. In terms of powering their plant, they could elect to use fossil fuels, for example, coal, oil, or natural gas, or they could decide to go for renewable energy such as wind, solar, tidal, geothermal, and others. Or, of course, they could combine both fossil fuels and renewables. So, I thought it would be interesting to show you what some of the students actually decided to go with. In terms of location, India or Australia, we have that 61% of them decided to go for India, and the balance 39% decided to go for Australia. In terms of the chemical products that were chosen and produced, we have that about 56% of them decided to go for glycols, which you remember is useful for making hydraulic brake fluids. A combination of glycol and amines, about 5.6% of them decided to go for that. Ethoxylates, which are useful in your hair shampoos and shower gels, 5.4%. Ethylene carbonate, which is useful for making lithium-ion battery electrolytes, 5.6% went for that. And for the ethanol amines, which again is a very important chemical in carbon capture and storage, nearly 28% of them decided to go for that. So that brings me to the end of my own aspect of the presentation. Hopefully that gives you a flavor of what is contained in the design brief in terms of sustainability. I'll now hand over to my colleague, Dr. Richard Neocluk, who will talk you through examples of sustainability analysis carried out by students. Richard, over to you.
Oh, thank you, Ademola. Let me just bring up my notes for a second. So hopefully that is coming through at the moment. So in this section, then I'll discuss then and give examples of sort of the sustainability analyses that the students then conducted throughout the project, so coming to the decisions that Ademola just discussed. So in this then, in this section, I'll discuss sort of then these analyses. These can really be grouped then by, say, the people and organizations, which is considered sort of on a power interest matrix, and a PESTLE analysis. Each of these I'll go into more detail in a second. Then say the process itself, so sort of the inputs and outputs, so the materials and energy required and the emissions or waste coming out. Then say interpretation of that process itself, and really then through hotspot analysis, prioritizing the management of the areas of the process that should be looked at. And then finally, sort of the impact also that it would be having. So what impact would the process have, say, with respect to global warming, climate change, but also any other emissions and wastes that are coming out of the process. So let us first look at then sort of PESTLE analysis. This would then be done by the students, at least within the project, sort of at the conceptual design sort of stage. So in the preliminary sort of part of the project. This is then sort of looking at PESTLE, just being an acronym, accounting for sort of political, economic, social, technical, legal, and environmental aspects. So this is then really considering the environment around the project or around your business, because it's changing sort of consistently. Using a PESTLE analysis and considering each of these components in turn then allows you to sort of do it in a more systematic way, and therefore sort of more fully capture and identify sort of key aspects of the environment, but also long-term trends that would or could impact their project. So just giving sort of some examples to these sort of political could be, say, the industrial strategy of the government, sort of for sustainable production changing. Economic, for example, there being a falling cost of your key sort of feedstock, your key sort of input into your process. Social, whether there's local acceptance of new industry. Technical, if there's an improving efficiency of a particularly key part of your process. Then legal, there being tighter emissions regulations. And finally, environmental, say if there's the impacts of global warming, but also things such as sort of pandemics, as we have unfortunately had over the last couple of years. Each of these then sort of can have a direct impact on your project, your stakeholders, and it's very important to sort of be aware of them and also plan for them. Moving on then to the stakeholder analysis. This is also sort of done by the students in the conceptual design stage, is really to answer these two questions. So sort of who has the power and interest to affect your proposed process? And secondly, why is it important then to actively consider stakeholders? To give this some structure, this is usually conducted, as shown here, a direct example from our students this year, actually, then on a power interest matrix. So you firstly identify sort of key stakeholders, and then you would rank them then on an interest and power matrix up your X and Y axis, so that you could then sort of better analyze sort of how each of these stakeholders should be sort of managed and considered going forward. In this instance, let's consider, say, the Bentham Corporation. So that's us, the teaching team, as Adam Muller said, who are acting as the clients of the students throughout the project. We have then significant interest in the project as key investors, and also as the managing company, we have sort of significant power to sort of change the project. And therefore, this, as the students had done, sort of requires sort of close management then of this stakeholder, and sort of informs then sort of how that relationship goes forward. The students in this instance also had very, very well sort of included sort of whether each stakeholder either supported, was neutral or against the project, which also gives an extra sort of dimension to how each of these stakeholders should be managed. While the students do not consider this within the project, it is practice also sort of, if you have the time and in industry, to do a more detailed strategy of how, if of all or most of the stakeholders would actually be managed. Moving on to then offsets. This, once again, within the conceptual design. An offset is then, sort of just to define it quickly, is a way of balancing then the project's impact. So here, if we consider, say, greenhouse gas emissions, if the project has emissions, which it is likely to have, then it's trying to sort of offset that against sort of cutting emissions elsewhere. This is not necessarily within the project, within sort of your process, but is outside of that. The benefits of this then are so that sort of the net impact, I suppose, on sort of society is actually starting to be more balanced out. And examples of offsets would, say, be reforestation, renewable energy, sort of capture then of, say, methane or other greenhouse gases, or even energy efficiency. Just an open question to yourselves that you do not have to answer now, but just for you to consider. Do you think that sort of there are any downsides to offsetting? And do you think that sort of offsetting as a long-term and large-scale solution? Just as, I suppose, a couple of pointers while you're thinking about that, if you consider that all emissions were offset, instead of also reducing them at the same time, do you think that there would be enough offsets available? Do you think we could reforest large enough areas or put enough renewable energy in order to balance all of those emissions? A downside potentially of offsetting then would also be that it could, if implemented poorly, incentivize then the management, so sort of putting in more sort of reforestation rather than preventing the emissions in the first place by careful design. Moving on then to sort of aspects that are conducted within the preliminary design. The first of these then to consider is really the life cycle assessments. So this is then a framework for assessing sort of the environmental impacts of our product, of our process. So considering both the inputs to our process and the outputs from the process. So in this instance, this is sort of with regards to whatever system boundary that you have defined. So here, this is around just the process itself. However, the definition of this system boundary is quite important, as it sort of does then define the scope of your assessment. The students within the project do a gate-to-gate analysis. So this is considering effectively just the process itself. So cutting off where the inputs, the material and energy, come into our process, and stopping where the products and emissions leave. There are others the students do not consider. So you could consider, say, cradle to grave or well to wheel as other system boundaries, for example. The next analysis is then a hotspot analysis, as I'd briefly touched on before. So the hotspot analysis is a tool that the students used to prioritize where they should adapt their process in order to reduce its impact. So really then to, as it says here, sort of find the low-hanging fruit. So those sort of savings with respect to emissions, for example, that would actually make significant savings in terms of the greenhouse gases, but actually require very little effort on our part. So the students actually then looked at the global warming potential here as sort of GWP, and put it in terms of the amount of CO2, so kilograms of carbon dioxide per sort of functional unit. So this is then sort of per ton of their product that they were producing. In this instance then, looking at the different components of their process, this group was then looking at monoethylene glycol production. So glycol production, as Adam Muller had previously stated, you could actually clearly see then that the first part of this production process, so the ethylene oxide or EO production, then attributes sort of a significantly larger amount of the global warming potential compared with the ethylene carbonate or EC, or later monoethylene glycol MEG production. Alternatively, you could then also look at sort of the emissions by species or chemical components that you have in your system. So importantly here, sort of, yes, sort of carbon dioxide is playing sort of 25%. However, despite the fact that methane actually is a very, very small percentage by mass of the material in the process, it attributes for 30% of the global warming potential of the overall process. This is really due to the sort of the multiplier effect that it has. So it has a 28 times greater sort of global warming potential than carbon dioxide over a 100-year period. And that is a large reason for why this share is so large. So it's important to consider not only sort of the carbon dioxide, but also other components such as methane that have significantly larger impact, even if they are in very, very small proportions of your overall process. Then still within the preliminary design stage, although this would be, as with others, sort of conducted sort of in the detailed design aspect of the process as well. Here the students conduct an energy analysis. This is then a tool that they use to reduce the overall consumption of energy in their process. So considering the simple example here, this is then considering a feedstock coming in that requires heating in order to enter the reactor. This reactor, the reaction occurring is exothermic, so that's generating heat. So our stream coming out is then hot. This unfortunately needs to be cooled in order for the separation to occur as we require in order to extract the product that we want. So at the moment, we're currently paying energy we're paying for sort of demand for energy in our heater and also in our cooler. But what we could do then is transfer heat then in order to save these energy requirements. So if we use the heat in this stream to heat up our feedstock, for example, then we could then reduce the energy consumption of both of these, or even eliminate one or both of them. So the students actually do this then for all of these streams, sort of considering all of the streams in their process. And this is, if you'd like to look at it more, using a method called pinch analysis. So finally, I suppose, sort of just to review sort of what the students felt about it, sort of their experience and feedback. We asked them a question not too long ago, actually, sort of this year, sort of a couple of weeks ago. Is there any particular aspect, activity of sustainability that should be either stopped, started, or remain the same? Here are just a very few sort of select examples, really then identifying that sort of the sustainability could be built upon from the previous task. That was really appreciated by one student. A good suggestion that we could also include something about the circular economy, so larger scale. Sorry. And then also finally, that the life cycle analysis for both of these comments was then seen as sort of both quite detailed, but then sort of also very useful and informative for their overall analysis of the process. I hope that you have found sort of this presentation useful and interesting. Please do sort of have a look over it again. If you would like further information on any of this or other aspects of what we do at UCL in chemical engineering, please look sort of either then sort of about the design project itself via the UCL's module catalogue, is the hyperlink that you could follow. On the general sort of Department of Chemical Engineering websites, or also sort of with either Twitter, Facebook, or LinkedIn, respectively.
Thank you for going through some of the ideas and concepts that we've been following this year with the students in terms of how we've set the problem to them, and also then in terms of some of the specifics that they have been saying. I believe you lost me at some point towards the end of my presentation, so I hope that there was a nice continual flow thereafter. And I believe there is a chat. There is a question. I don't know if you can see that.
Yes, so specifically about UCL, do you only offer a biochemical engineering course rather than a pure chemical engineering? Michaela, would you be able to answer that one for us?
At UCL, there's two separate departments. There's a Department of Chemical Engineering and there's a Department of Biochemical Engineering. And you can do an undergraduate degree in either of those departments. So either if you go to the UCL website and look at the various departments, you can either look directly on the chemical engineering website or on the biochemical engineering departmental website as well.
Is it more a priority to make as much product or least pollution? Or is it mainly about sustainability of the process? Ademola, you're smiling, so do you want to take this one?
Yeah, I will. Yeah, so I mean, as chemical engineers, I mean, the way we set out to design our process is as best we can, we try to design out waste, okay? So don't create the waste in the first place if you can help it, okay? And of course, at the forefront of our minds as well is sustainability and safety when we're also putting together the process. So we balance all these together. Of course, yes, we do want to make a profit, but I mean, we do place sustainability and safety first as best we can before we take on profit next. So yeah, design out the waste where you can, okay? Or where you cannot, of course, minimize it, okay? So sustainability is out there on top, along with safety.
Great, thank you. Just another one in the Q&A there. So how would I choose between chemical engineering or material science? I don't mind taking this one. I think I would probably speak for each of us, but sort of I think that's going to be based really on sort of your interest first and foremost. yes, while there are sort of some similarities sort of between definitely both of those, I think sort of careful consideration, there are some differences, and you should look, I suppose, looking at sort of the prospectuses, and then sort of similarly sort of say UCL module sort of catalog, to see then sort of which you feel sort of you have greater interest in. That would definitely, I think, sort of inform which course you should take. As if you do that, sort of you'll get more out of the course and enjoy it more, I would suggest. Hopefully that's answered your on there.
What I would go back to, if there's no more questions, then is just to say that one of the previous questions about what's more important, sustainability or economics and so on, that raises an interesting point in the chemical engineering design, that it's always about trade-offs. That in engineering, there are multiple solutions, many different solutions, some which focus on more on one aspect or another aspect. And one of the challenges of chemical engineering design is that it's such an open-ended problem, and you're continually looking at these trade-offs and trying to determine what is a viable and good solution, and for whatever reasons, and justify the reasons that that can be. It's not a case of there is only one solution.
I couldn't agree more. Yeah, I suppose adding further to that, as it is sort of a very open question as well. Just to inform you, I suppose, sort of within the design specification that Ademola had mentioned, that we had actually then capped, we'd given a range of feedstock, sort of mass, sort of flow rate that the students had availability of a key component. So that then sort of dictated to a large degree how much product they could make, at least on the maximum and minimum side of things. If that gives a little bit more context to that. There are sort of understandably sort of economies of scale for producing more in many, if not sort of most instances. So you could sort of get sort of financial benefits from that, sort of, or even sort of sustainable ones. This could sort of then help actually give you more capital that you could employ to make your process sort of greener. A way of considering that more actively that you could look at is sort of the triple bottom line, actually, that then sort of tries to actually sort of monetizes sustainability a little bit, and then you could take that into your economic considerations as well.
Yeah, thanks, Richard. I think that just shows how wide the scope of sustainability is, and it's not a case that all of those aspects are incorporated in the course that we deliver, but some of those aspects are incorporated in the course that we deliver, and different emphasis can be placed on it.
Just want to say thank you again to the design team, and hope everyone's enjoyed the virtual lecture. Fantastic. Okay, well, I will say goodbye and thank you.
Thanks for coming today.
Thank you.
Thank you. Bye-bye.
Bye.